Welcome to our unit on compounds, where we'll learn about the periodic table and how elements bond together. So how was the periodic table created? Well, in the 1700s and 1800s, scientists spent lots of time discovering new elements and recording their properties. Chemist John Newlands noticed a pattern while looking at these elements. When arranged by atomic mass, the elements seemed to repeat properties every 8 elements. He called this the law of octaves. Newlands got the concept of octaves from musical notes, which repeat every 8 notes. So he was saying essentially that this first compound was like the 9th compound, and the second compound was like the 10th compound, and so it worked like a piano keyboard or piano keys, where this is C and then another C over here starts the next octave. His discovery was controversial because it only worked for the first 20 elements. Then Russian scientist Dmitry Mendeleev improved on Newland's work by arranging elements by properties, but leaving holes where he suspected that undiscovered elements would go. So this is his periodic table, and he left holes where he thought that undiscovered elements would be placed based on the properties of the current elements that they knew existed. He knew that there must be some gaps. After Henry Moseley discovered the atomic number, though, Mendeleev's periodic table was adjusted. By arranging by atomic number, there was an even clearer pattern of chemical properties. So as you can see, of course, now the current periodic table is organized by increasing atomic number, starting with hydrogen, which has an atomic number of 1. This is summarized by what we call periodic law. Elements fall into groups with similar properties when organized by atomic number. So that's the periodic law. So how is the periodic table organized now? We know it's organized by atomic number, but what else can we tell about the periodic table? Each horizontal row in the periodic table is called a period, and each period has an energy level, which we designate as N, which correlates to the location of electrons in the Bohr model. Each column is a group or family of elements, and each group has similar chemical properties. So taking a look here at our periodic table, here are our periods 1 through 7, and those correspond with energy levels. Row 1 has 1 energy level, row 2 has 2 energy levels, and so on. And groups are numbered across the top, and there's 2 different systems of naming groups. This Roman numeral one is an older version, and the regular numbers are the new way of naming. You may see either one depending on which periodic table you're using. Generally, we're going to use the new numbering system though. And some of these groups have special names. Group 1, the first column, contains hydrogen and alkali metals. So hydrogen is not a metal, but it's placed there because it has 1 valence electron, as do all of the other alkali metals. Group 2 is known as the alkaline earth metals, which got their name because compounds made from these elements were able to withstand fire and were insoluble in water, and scientists used to call that type of element an earth element. Group 17 is known as the halogens, which are highly reactive, and we'll learn why in a little bit. And then group 18 at the end here is the noble gases, and those are very unreactive. They do not like to form compounds. In the middle, groups 3 through 12 are called the transition metals. And down here we have the lanthanoids and actinoids, and with lanthanoids being the first row here and actinoids being the second row. And these actually fit up here in the transition metal category. So you can see barium has an atomic number of 56 and lanthanum has an atomic number of 57. So it fits right here. But in order to compress this periodic table a little bit and make it not excessively long, the lanthanoids and actinoids have been placed below the rest of this periodic table just to condense it a little bit. But just know that they are transition metals and they do fit right here. So in summary, periodic law is the basis for the modern periodic table, which is an adjusted version of the one proposed by Mendeleev. Elements are organized into rows or periods and groups that have similar chemical properties. Why do atoms in the same group have similar properties? So we've discussed that they do have similar properties in the same group, but why exactly is that? Remember, first of all, that valence electrons are those in the outermost energy level for an atom. So we discussed this in our discussion of atomic structure, that valence electrons are found in the last or outermost energy level for an atom. And different atoms have a different number of energy levels, but whatever the last energy level is, what the electrons in that energy level are the valence electrons. Valence electrons are important because they determine how elements react and combine with other elements. Since the valence electrons are the same for each group, the chemical properties for elements in that group are similar. So this diagram shows the electron dot structure for the main group of elements in the periodic table. So you can see the valence electrons here for the first group are all 1. There's 1 valence electron for all of those elements. And group 2 is going to have 2 valence electrons, and so on, with the exception of the transition metals. So valence electrons are the same throughout a group, and they increase across a period. So the same here, all 1 valence electron. Here we're increasing 1 valence electron, 2, 3, 4, 5, and so on, all the way to 8 at the end of the periodic table. Helium is the exception to this rule, but it has similar properties to the rest of the noble gases because it has a full outer energy level. So here's helium. It has 2 valence electrons, but the rest of these noble gases have 8. And that's because it only has 1 energy level, and that first energy level holds 2 electrons, and so it is a full energy level. So it's going to have the same properties as these other elements that have full outer energy levels. So the valence electrons are what cause the similar properties in the groups throughout the periodic table. What patterns are found in the periodic table? So when the periodic table is organized by atomic number, there are patterns or trends that are found throughout it. So not just in the groups and the periods themselves, but if we look at the periodic table as a whole, we'll see some patterns. Periodic trends are predictable patterns within the periodic table, and there are 4 major periodic trends. The first is atomic radius. So radius, remember, is the distance on a circle from the center to the outer edge. So this generally works as you think of a normal circle, but if these are atoms, the outer edge of this atom and where those electrons are actually located is sort of a tricky thing to measure because the electrons are not exactly in a specific orbit. So what scientists do instead is they measure the distance between two nuclei of an atom that has, or an element, sorry, that has two of exactly the same atom. So atomic radius is half the distance between two nuclei of the same element. So measuring the distance between these nuclei and then dividing it in half gives us the radius. And that's a little bit easier to measure than if we just did one specific atom. Atomic radius decreases across a period and increases down a group. So if you look at this image of the periodic table, you can see how the atomic radius changes across a period. It is decreasing, same here, and down a group, it is increasing. And the reason for this is because across a period, the number of protons increase. So if you can picture here, the atomic number for potassium is 19 and the atomic number for krypton is 36. So we're increasing the atomic number across this periodic table, across the period. And as we do that, because atomic number is the number of protons, we are increasing the number of protons, positively charged protons, across this period. And because they have a greater positive charge, then these atoms over here are able to draw the negatively charged electrons closer into the nucleus. So these atoms over here have fewer protons and they don't draw those electrons in as tightly, and these have more protons and are able to draw in those electrons a little bit more strongly. Moving down a group, new electron orbitals are added, making the atom bigger. So as we've discussed, the elements at the top here in this first period have one energy level, only one energy level. The elements in the second period have two energy levels, three in the third, and so on. And so there are more and more energy levels being added as we go down this group. And that means that the radius of the atom is actually getting larger because there are more energy levels, and therefore the electrons are further from the nucleus. So generally, we describe this trend as increasing from right to left. These are smaller, so increasing from right to left and increasing from top to bottom. The second trend is electronegativity. And electronegativity measures the ability of an atom to attract electrons from other atoms towards itself. And electronegativity increases from left to right on the periodic table and bottom to top. So this is opposite of the atomic radius trend. And the most electronegative element is fluorine. So as we are moving up towards fluorine, the electronegativity is increasing. And as we are moving from left to right towards fluorine, the electronegativity is also increasing. And the reason for this is related to atomic radius. So the atomic radius is smaller over here because the nucleus has a really strong pull on the electrons, and so that makes the electronegativity, or the ability to attract electrons, high because that atomic radius is pulling strongly. And down a group, the electronegativity is decreasing here because as the atomic radius is increasing, the valence electrons are further away. So these elements at the bottom that have a number of energy levels are experiencing a weaker attraction. So they're not actually able to attract electrons very strongly because the electrons are being added pretty far away from the nucleus. So we're going to write our trend as increasing in electronegativity as we go up the table and increasing from left to right, completely opposite of the atomic radius trend. The noble gases, however, do not have electronegativity values because they do not form compounds with other atoms. Because they have full outer energy levels, 8, or in the case of helium, 2 valence electrons, they are not interested in gaining or losing electrons. And so they're very stable, and therefore they do not have electronegativity values. Electron affinity is the tendency of an atom to gain an electron in order to form a negative ion or a charged atom. So these are going to be elements that gain electrons easily. And electron affinity increases towards the right, from left to right, and towards the top, so bottom to top, same as the electronegativity trend. So the electron affinity increases as we move from bottom to top because there are fewer, similar to electronegativity, there are fewer energy levels at the top, and so the nucleus pulls a little bit more strongly up at the top elements here, and so it's able to pull electrons. But it also increases from left to right, and that's because elements on this side have a much more condensed nucleus from that atomic radius trend, and so they are able to pull on electrons, both their own as well as other atoms' electrons, strongly. However, noble gases do not have electron affinity values because they don't gain electrons because their valence shells are full, and so they do not have an attraction to add electrons to their valence shells. Ionization energy is the fourth trend, and this is the amount of energy required to remove an electron from a neutral atom's valence shell. So similar to electron affinity, where we were trying to gain electrons, this is the ability to remove an electron. And it becomes more difficult to remove electrons from atoms that are further towards the right and towards the top. So the amount of energy is increasing from bottom to top and left to right. This is due to the close distance of the valence shell electrons to the protons in the nucleus. So just like electronegativity and electron affinity, that stronger pull of the nucleus is going to make it more difficult to remove the electrons from some of these atoms. So increasing ionization energy is from bottom to top and left to right. The ability to remove one electron is called the first ionization energy. So if we were to remove one electron, successive electrons that are removed require more energy, and so they're going to have a higher second ionization energy because they are being pulled even more strongly towards the nucleus because there's going to be a greater positive charge compared to the remaining negative charges that are left after this electron is pulled off. So if we use one arrow rather than two for each of these trends, it helps us to simplify the trend a little bit. So atomic radius is increasing from the top right corner of the periodic table down to the bottom left. Electronegativity and electron affinity are increasing from the bottom left corner to the top right, except for the noble gases, which don't have the affinity to gain or lose electrons. And ionization energy is increasing from bottom left to top right as well. And the noble gases do have ionization energy, so they're included in this arrow because it requires a lot of energy to remove electrons from that full shell. In summary, elements within the same group generally have the same number of valence electrons. And the periodic table also shows trends such as atomic radius, electronegativity, electron affinity, and ionization energy. So far, we've discussed that noble gases are exceptions to a couple of these trends. So what is it that makes noble gases so unusual and so different? And it's because they are chemically stable. So let's talk about why that is. Noble gases do not often combine with other atoms to form new compounds because they have a full valence shell of electrons. This makes them the most chemically stable elements. So as we mentioned when we were talking about periodic trends, they don't want to give up electrons and they don't want to gain electrons because they already have full energy levels. So in each of these Bohr models, you can see that the outer energy level is full. For helium, that outer energy level is simply the first one. Since that only holds 2 electrons, that energy level is full. For some of these larger atoms, the second energy level is full, and the number of electrons in each shell is given in the top right corner here. So you can see that the first energy level is holding 2 and the second is holding 8, and these are all full energy levels. Why do other atoms form compounds? Well, atoms rarely exist as independent particles in nature. Even though we've been discussing them as the basic unit of matter, they rarely exist by themselves. Most substances are made of combinations of atoms that are held together by chemical bonds, and we'll discuss the types of chemical bonds all throughout this course. But as you can see, even oxygen gas is a combination of 2 atoms of oxygen. So the formula for oxygen gas is actually O2. And these 2 atoms of oxygen are bonded together by sharing electrons. A chemical bond is a strong force of attraction between the nuclei and valence electrons of different atoms that binds the atoms together. So this is how we form molecules, which are the basic component of compounds. Chemical bonding allows atoms to form stable chemical compounds. So even though they may be slightly unstable as individual atoms, because they readily gain or lose electrons, when they bond with another atom, it makes that compound stable. Here's 2 examples. In this bond, sodium's valence electron here, the red one, was passed to the chlorine atom. And as the sodium atom lost an electron, because electrons are negatively charged, it became more positively charged. And as the chlorine atom accepted that electron, which is negatively charged, it became more negatively charged. And so these 2 atoms are attracted to each other now, and that's what helps to form that bond. In this arrangement here, 2 chlorine atoms are sharing a valence electron, which allows them to both seem like they have a full valence shell. By sharing that 1 electron, they're able to have that stability. So what is an ion? An ion is an atom or molecule with a net electric charge due to the loss or gain of electrons. So these 2 atoms up here are ions. This is a positively charged ion. This is a negatively charged ion. A positive ion is called a cation, and a negative ion is called an anion. So here are some examples. Hydrogen only has 1 electron. If it loses that electron, it becomes a positively charged ion, and we write that with a little charge up at the top right corner. So H plus is a positive cation of hydrogen. If chlorine gains an electron, like it did in the previous slide, it becomes a negatively charged ion or an anion. And if lithium loses an electron, it becomes a positively charged cation, which we write as Li+. And as you remember from our discussion of the periodic table, the elements on the left-hand side, the metals like lithium and hydrogen, has similar properties, even though it's not a metal, but they are willing to lose electrons more readily. And chlorine is on the right side of the periodic table. It's a non-metal and it accepts electrons readily. So that's what causes them to either become a cation or an anion. Since electrons are negatively charged particles, when an electron is gained, the atom becomes more negative. When electrons are lost, the atom becomes more positive. So what is noble gas envy? This is a made-up term that we use to explain a situation that commonly occurs here when we're forming compounds. Well, atoms will gain or lose electrons to achieve stability. And as they are gaining and losing electrons, they're forming compounds with other atoms. This causes the ion to have a full valence shell. If they are losing one outer valence electron, they're now left with a full valence shell in that smaller energy level. The atom's new electron configuration is the same as a noble gas. So this phenomenon is sometimes known as noble gas envy. So let's look at an example here. If we're talking about chlorine gaining an electron, it does have 7 electrons naturally in this outer valence shell. But if it gains an electron, now it has 8. And so yes, it now becomes a negatively charged ion, but it also has the configuration of a noble gas with this full outer energy level. So this is actually the configuration of argon. But since we're not changing the number of protons in the middle of that chlorine atom, it's not changing into argon. It just now has the same number of electrons as argon, which is a stable noble gas. So that's why we call this noble gas envy, because these atoms are working towards getting a full valence shell like a noble gas. So in summary, noble gases are stable because they have full valence shells. Some atoms can mimic the stability of noble gases by gaining or losing electrons. The atoms are then called ions. So how do ions, or charged atoms, form ionic bonds? Well, the attraction between the positively charged cations and the negatively charged anions form ionic bonds. The overall charge of the molecule is electrically neutral because cation and anion charges balance each other. The chemical formula for an ionic compound represents the simplest formula of the compound. It is called the formula unit. So if we're looking at our easiest example here of an ionic bond, sodium and chlorine, which forms sodium chloride, which you know as table salt. The sodium ion forms when the outermost electron is given from sodium to chlorine, giving that sodium a positive charge and the chlorine a negative charge. And then they are attracted to each other and form an ionic bond, and that becomes NaCl. So these two ions are attracted to each other, bonded together by that opposite charge, and form the compound or formula unit of NaCl. Ions in an ionic compound lower their potential energy by forming a crystal lattice where the positive and negative charges are balanced. So if you picture a bunch of positively charged sodium ions and negatively charged chlorine ions together, not only are they attracted to each other, but they're attracted to the other ions around them. And so they eventually gather together and form this crystal lattice structure. And the crystal lattice is responsible for many of the properties that ionic compounds share. So what exactly are those properties? Well, ionic compounds are made from a metal and a nonmetal. We've discussed that the metals give up electrons and the nonmetals on the right side of the periodic table gain electrons. So ionic compounds are made from a metal and a nonmetal. They have high melting points and they dissociate into ions when dissolved in water. Solutions of ionic compounds, because they have dissociated into ions, these ions conduct electricity, but solid ionic compounds do not. So here's an example. This is a crystal of lithium fluoride, and when it is dissolved, it dissociates into the following ions: positive lithium ion and a negative fluorine ion. Because this lithium has given up an electron to the fluorine atom. So this liquid here would conduct electricity because these charged ions are able to conduct electricity, but the uncharged crystal lattice of the solid ionic compound is not able to. So what determines an ion's charge? So far we've been talking about positive one charge and negative one charge. That is not always the case. An atom's ionic charge is determined by whether it gains or loses electrons to reach a full valence shell. So as we mentioned, elements on the left side of the table lose electrons, and elements on the right side of the table gain electrons in order to reach that full valence shell. If they have less than 4 valence electrons, they're going to lose electrons. It's going to be more efficient for them to lose those 1 to 3 electrons than it would be to gain up to 5 and to form that outer shell. And so these atoms are going to have a positive 1, positive 2, and positive 3 charge. If they have more than 4 valence electrons, which are going to be these atoms on the right side of the periodic table, they're going to gain electrons. It's more efficient for them to gain a couple to fill that outer shell than to lose a bunch. So these groups are going to be -3. Every element in this group is going to gain 3 electrons to fill that outer valence shell because they have 5 valence electrons. These elements are going to gain 2 electrons since they have 6, and that gives them a -2 charge. And this group of elements is going to gain 1 electron, giving them a -1 charge. So all of the elements in these groups are going to have these particular charges. And since you know about the valence electrons, you can understand why these charges exist. But as we go forward in the class, we generally discuss the charges a little bit more commonly, and we don't necessarily look at all of the valence electrons every time. So because calcium has 2 valence electrons here, this is the group with 1 valence electron, this is the group with 2 valence electrons, it will lose them and give calcium a charge of +2. The charges of cations and anions will balance to form an overall charge of 0 in an ionic bond. So let's practice. How would beryllium and chlorine combine? Beryllium is right here in a +2 category, 2 valence electrons. Chlorine is over here in this group, and it has a charge of -1. So we've got beryllium on one side with a +2 charge. We would need 2 -1 charged chlorine ions to balance that out. So 2 anions for every 1 cation here, just to balance out these charges. That would give us a formula of beryllium chloride, or BeCl2, and this 2 is called a subscript. It shows that there are 2 atoms of chlorine, so we've got 2 chlorine atoms here in this compound, 1 beryllium atom. The beryllium does not have a subscript because the 1 here is understood. We don't ever write a 1 in a chemical formula. We just leave it as is. So 1 beryllium atom, 2 chlorine atoms in order to balance those charges. Here's another example. If we have magnesium, which each have a positive 2 charge, if we look back here, magnesium is found right here below beryllium. So magnesium has a +2 charge. In order to give us +6, we need 3 of these, and that would balance out 2 -3 ions of phosphorus. And so then our charges here could balance +6 and -6. So when we combine magnesium and phosphorus, the formula is going to be Mg3, 3 atoms of magnesium, P2, 2 atoms of phosphorus. And there is a shortcut method to doing this. If you look at the charges of each of these atoms or ions, magnesium has +2, phosphorus has -3. We can actually just swap those numbers and put the 3 by the magnesium, meaning that there are 3 magnesium necessary to balance that out. And the +2 for magnesium gets put over here next to the phosphorus. And that means that there are 2 phosphorus atoms that need to balance. And so as long as you understand what is happening and why we balance like this, then you can use that shortcut of swapping the charges. So let's practice. On a piece of paper or on the back of your notes, write the formula for the following ionic compounds using the periodic table for reference. So go back and look at your periodic table. Find the charges for each of these elements and create the chemical formula that's formed when these combine. So find calcium and find bromine, figure out the charges, and then write the chemical formula. Pause the video until you've completed it, and then you can come back and check your answers. Okay, so if we check answers, you should have CaBr2 when calcium and bromine combine. Sodium and phosphorus should be Na3P, and that's an understood one, but we're not going to write it. Mg and O actually combined because they both have charges of 2. Magnesium has +2, oxygen has -2. They would combine as Mg2O2 if we were just to swap our subscripts, but we always reduce it or write it as MgO with just one atom of magnesium and 1 atom of oxygen, because that's really all it needs. 1 magnesium atom with a +2 charge will balance out 1 oxygen atom with a -2 charge. And then beryllium and phosphorus will combine into Be3P2. In summary, ionic bonds form between 2 oppositely charged atoms or groups of atoms. These bonds form between metals and nonmetals to create a crystal lattice, which causes properties such as a high melting point. So how do we name these ionic compounds? Well, ionic compounds are named for their cations and their anions. The first word in an ionic name is the cation, and the second word is the anion, with a little bit of an adjustment. So as an example here, sodium and chlorine form an ionic bond. In the ionic compound NaCl, sodium loses an electron and becomes the cation. Chlorine gains an electron and becomes the anion, and this compound is called sodium cation first chloride for the chlorine anion. What are type 1 ionic compounds? Type 1 cations are compounds that have only one possible charge, and these are most straightforward for naming. All elements in group 1 will lose one electron. They always have a +1 charge. All elements in group 2 will lose 2 electrons, so they always have a +2 charge. The transition metals have a variety of charges, and even some of the elements in group 13 over here that we said generally have a +3 charge, some of those don't always have a +3 charge. Aluminum, however, always has a +3 charge, found right here. Zinc always has a +2 charge, right here. Silver has a +1 charge, right here. And cadmium, right next to it, has a +2 charge. So these are our type 1 cations that always are going to have that same charge. So how do we name those type 1 compounds? Well, as I said, we start with a cation, and if it's a simple cation, only one element, then we use the name of the element, for example, sodium. And then we add the anion. If it's a simple anion, only one element, then we change the ending of that element to "ide." So in other words, we've now got sodium, change chlorine to chloride, and that's how we get NaCl as sodium chloride. Now, these don't always bond one atom to one atom, which is why we're calling these simple cations and simple anions. We'll get into more complicated in a little bit. But for right now, if we're just talking about two elements together, one is a cation and one's an anion, it's a very simple naming process. So let's practice. Name these compounds. Pause the video until you figured it out. Okay, these are straightforward. Calcium, sulfide. Remember, we know that this is a different element because there's capital letters here. So Ca is one element, S is a separate element, calcium sulfide. Doesn't matter here that we've got a 2 after the chlorine. We're still going to name this barium chloride. Same thing here. Doesn't matter that we have a 2 after that F. That's just balancing our charges, but it does not change the naming. And so we're going to have magnesium fluoride. Those are pretty straightforward. When you're working backwards from name to formula, don't forget to balance your ion charges. So practice this one. What is the formula for lithium nitride? So now I'm giving you the name and I want you to work backwards. You need to figure out what these two elements are and then balance your ion charges to make sure that you have the correct subscripts when you're writing that compound formula. So pause the video for a second and figure that out. Okay, so lithium has a +1 charge. Nitride means that we have nitrogen as our anion. Nitrogen has a -3 charge. And so our example here is going to be lithium nitride with a formula of Li3N. To balance those charges, we need 3 lithium atoms for every 1 nitrogen atom. Here's a couple more to practice. Write the formula for calcium bromide. Okay, our calcium bromide formula should be CaBr2. We need 2 bromines to balance out that positive 2 charge of the calcium cation. Okay, so that's our easiest way of naming ionic compounds. But what are type 2 cations? So how do we make this a little bit more complicated if the charges are able to change for some of these cations? Well, type 2 cations are elements that can have several charges. They don't always lose the same number of electrons. These are the transition metals on the periodic table, and as I mentioned, some of the elements in group 13 as well have a variety of charges a little bit further down the table. And the exceptions that we already talked about are not, even though they are transition metals, they are not part of the type 2 cations because they are always going to lose the same number of electrons. The charge of the cation is expressed as a Roman numeral for type 2 cations. So we use Roman numerals here to represent our charges. Still, just as we talked about before, cation and anion charges must balance to 0. So here's an example. Cobalt, and then we call this 2, cobalt 2 with a Roman numeral 2 here. Bromide is cobalt with a plus 2 charge, and bromine. So we've got cobalt plus 2 and bromine, which has a minus 1 charge. Those are going to balance out to form cobalt bromide, which is the COBr2. So let's practice. We've got some type 1 and some type 2 practice here. On scrap paper or the back of your notes page, write the name of each of these ionic compounds. So pause the video until you've figured it out. Okay, the first one is lithium bromide. Second is calcium sulfide. The third compound here is potassium chloride. And the fourth is sodium fluoride. Those are all type 1. And if we continue with a little more practice here, figure out the names of these compounds. Pause the video until you figure them out. Okay, the first one is tin 2 bromide. So we can figure out that tin here, which is a transition metal, has a plus 2 charge because bromine has a minus 1. So if there's 2 minus 1 bromines, then this must be a plus 2 tin. And so we write tin, Roman numeral 2, bromide. The next one is similar, but since we've got Br4 here, that must mean that bromine with a minus 1 charge, we've got an overall charge of minus 4 for bromine, and therefore this tin must now have a positive 4 charge. So now we write tin, 4, bromide. Next one is chromium 2 oxide. Oxygen has a minus 2 charge, so this chromium, if they're balanced out, must be a plus 2 charge, chromium 2 oxide. And then for this last one, chromium 3 oxide, it would take a charge of plus 3. 2 of those would give us a plus 6, and so that balances out with our minus 6 of 3 oxygens. Since each of those oxygens has a negative 2 charge, 3 of them would be minus 6. And so we need to make this equal positive 6, which means that each of these would need to be a plus 3 charge. So chromium 3 oxide. All right, let's work in the opposite direction. If I give you the name, can you determine the formula? So find the formula of these compounds and pause the video until you've figured it out. Okay, first one, silver sulfide. Silver has a +1 charge, and so it takes 2 of those to compensate for the -2 charge of sulfur. Sodium iodide is going to be NaI. That one's a type 1, so that's pretty straightforward. Aluminum fluoride. Aluminum has a +3 charge, so it will take 3 fluorines to balance that out. Lead 2 oxide. This 2 means that our lead here has a +2 charge. And so since oxygen has a -2 charge, these are going to balance out. Copper 2 iodide. Copper has a +2 charge here from our Roman numeral, so it takes 2 iodines to balance that out. Tin 4 oxide is going to be SnO2 because this +4 from the tin needs to be balanced out with 2 of the -2 charge oxygens. So in summary, ionic compounds are named by their ions. The cation is first, followed by the anion, which changes to "ide." Roman numerals identify the charge for most transition metals. Okay, so far we've mostly been talking about atoms taking and giving electrons, but sometimes they also share electrons. So why do they share? Well, covalent bonds are created between atoms when atoms share electrons. The electronegativity of an atom is a measure of the atom's ability to attract electrons. So we talked about this with periodic trends, but the electronegativity of any atom is its ability to pull electrons from another atom. And sharing a pair of electrons results when the nuclear pull of one atom is not strong enough to take an electron from the other atom. So if the electronegativity isn't high enough for an atom to totally pull an electron off of another atom and create an ionic bond, then they're going to share those electrons instead. And covalent bonding usually occurs between nonmetals. So here is methane, which is CH4 as an example, and hydrogen with its 1 electron is sharing with carbon. Carbon has 4 valence electrons, and so it is sharing with 4 hydrogen atoms. It's sharing those 4 electrons from the hydrogen atoms to give a full valence shell to carbon. What are the properties of covalent compounds? So we talked about the properties of ionic. What are the properties of covalent compounds? Covalent compounds have low boiling and melting points. They are soft and flexible because they don't have that brittle crystal lattice that the ionic compounds do. They do not conduct electricity, and they are insoluble in water. Wax is a good example of a covalent compound. I'm sure that you know from your life so far that wax is insoluble in water. If you put a candle in water, it's not going to slowly dissolve. It doesn't conduct electricity, and it is soft and flexible. Obviously has a low melting point, or we wouldn't be using it for candles. How are covalent, or molecular is another word we use for covalent compounds, how are these named? So molecular compounds are composed of nonmetal atoms that are covalently bonded. So when you see 2 nonmetals together, that should be an indication to you immediately that this is a covalent or molecular compound. And it has different naming rules. So we don't have cations and anions like we did in ionic bonding, and so we can't name them in the same way. We're going to start with rules for naming binary covalent compounds, or compounds that just have 2 elements in them. The first element in the formula uses the name of the element. So So that's easy. The second element is named by taking the stem and adding the suffix "ide." So far, very similar to ionic compounds, but here's the difference. Prefixes are used to specify the number of atoms in a molecule. So we are going to now name these differently because we are going to count the number of atoms of each type. And the way that I help students remember that is that covalent compounds we count. So both of those start with C. If you're talking about an ionic compound, you're not going to count how many atoms are in it. And when we write that, we use molecular prefixes, and these are our prefixes. If we have one atom of an element, we're going to write a prefix of mono. 2 is di, 3, tri, 4, tetra, 5 is penta, 6 atoms is hexa, 7 hepta, 8 octa, 9 nona, 10 deca. We do not use mono in front of the first element. So if there's only one atom of that element, then we are not going to put mono in front of the first element. Generally, we start with whatever the central atom is in our naming. And so if we're looking at this atom here, or this molecule here that has 1 carbon atom and 4 fluorine atoms, we are going to start with that central atom of carbon, and there's only 1 carbon. Since we're not going to use mono in the front of that first word, this is going to be just carbon for our first word. And then second word is our 4 fluorine atoms, and 4 is tetra. So this is going to be carbon tetrafluoride. Okay, let's practice. So practice naming these compounds on a separate piece of paper or on the back of your notes. These are all covalent compounds, so we are going to count exactly how many atoms we have of each element. So pause the video, practice this using the prefixes that I just discussed. Okay, first one is tetraphosphorus decasulfide. Tetra for 4, phosphorus, deca for 10, and then we change the ending to ide. Tetraphosphorus decasulfide. Second one is sulfur dioxide. We do not put a mono in front of this because it's the first word. Phosphorus pentachloride. Chlorine trifluoride, and dinitrogen trioxide. Okay, here's a little exception to the rule here. How are double vowels changed? So if we have a prefix like deca that ends with an A, and then we have an O that comes after it, usually for oxygen, we aren't going to we're not going to say decaoxide. We're going to say, we're going to combine that to make it a little bit easier to say. So if you have an AO combination or a double O combination, you're just going to change it into an O. So here's 2 examples. Dichlorine for our 2 chlorines, heptaoxide. That's our AO combination. We're going to change it to just dichlorine heptoxide, which is a little bit easier to say. Another one here, H2O, which you generally know as water, but it does have a scientific name. Dihydrogen monoxide is going to be changed to dihydrogen monoxide. So try these last 2, pause the video, and then come back and check them. Okay, this first one is tetraphosphorus hexoxide. And the second one is carbon monoxide. So in summary, covalently bonded nonmetals form molecular compounds. When naming molecular compounds, the first element is named, followed by the second element changed to "ide." Prefixes are used to indicate the number of each atom in the compound.